Well, good afternoon. It's a real pleasure to be here with you. Thank you, Jeff, for inviting me. I would like to talk about how we should measure the value of enhancing water supply reliability. And to put you right in the hot seat, the question really is, imagine yourself the GM of a water agency, and you're considering, and you're here in Southern California, so most of your water is imported, or at least a significant share of it. And you are considering a project like, a local source development project like DeShazo. And you have been asked to demonstrate what the benefits of improved reliability of that water, that new water source is going to be. You need to answer the question, when will it pay off, if at all? What future drought impacts are going to be avoided? What peace of mind are we buying? And how are we going to communicate these benefits of reliability to our board members, to our ratepayers, to our large customers? Right? So that's the focus. And it's tricky because when we think about developing local water sources, we can identify a couple of values that they contribute. One is improved reliability under certain conditions. I'm going to talk about those conditions in just a minute. But those benefits come in avoiding or limiting the severity of future shortages or droughts. The second is that local source, while it may be expensive in the early years, may become less expensive than imported water in the future years. So you have avoided future costs that you have to figure out how to calculate. Right. So that's the second value component that often gets overlooked. The third one is one that we're all used to thinking about, which is, okay, it could simply increase the total amount of water supply that we have available. Right. So that's actually not a problem. That third value component is not something I'm going to focus on today. It doesn't characterize many of the water agencies. As you just saw, consumption is typically flat and sometimes declining for most of the water agencies. So that third component really isn't the focus. But 1 and 2 are actually a challenge for most water agencies to evaluate. And what I want to do today is make a proposal, a short proposal to you about how we might go about valuing improved reliability and identifying if there are avoided costs, what those avoided costs to ratepayers are of adopting and developing local water sources. I then want to take the results of the Phase 1 and Phase 2 approach and incorporate them into financial decision making about when, how much, and which local water sources one might develop. Right? And this is going to be somewhat of a schematic argument that I'm going to make, hopefully sketching out what the steps would look like so that you're convinced that it's actually feasible to implement. Now, the reliability value of a local source depends on how much of it's going to be available when other imported sources are less available. So is it going to be available during a period of shortage? And that depends largely on whether that local source is uncorrelated with imported sources from either the Colorado or from the state water plan. So really reliability and the benefits of improved reliability emerge only if that local source, its availability is uncorrelated with the things that are causing the regional drought, the regional shortages, right? So ocean desal is the classic example. Groundwater storage and in enhancing storage capacity through stormwater capture and aquifer remediation are also, they have some of these characteristics for periods of short drought, right? Moderately correlated with droughts are gray water, wastewater recycling, and things like that. Their availability drops and the cost of producing them goes up during periods of drought for reasons that I won't focus on now, but we can discuss later on. So the first thing I want to do is propose a method for valuing improved reliability from this local source. And the first thing that we have to do is to figure out how we're going to measure reliability. And there have been quite a few recent in the literature sort of advances. And probably the easiest way to think about this is reliability measured in terms of the number of days or years of a shortfall, and then the intensity or severity of that shortfall. Okay, so these are units of time during which we're experiencing various degrees of shortages. And then we need to ask, well, what's the future cost? Let's imagine we've got a 20-year planning horizon that we're dealing with, just for the sake of simplicity. How do we think about the cost of future unreliable supplies and falling short of what we need? Well, what's interesting is a lot of the early costs during a period of shortage are borne by the agency without the customer hopefully ever knowing that they're experiencing a shortage, right? You guys as water agency GMs and supporters of these agencies, you don't want your customers to suffer. So what do? You incur higher operational costs, lower revenues, higher financing costs. Other kinds of emergency actions are taken that increase the cost to you and eventually get passed on to customers, but aren't immediately manifest. In cases of severe or prolonged droughts, then we need to think about measures to customers of the cost of adapting to these states of unreliable water supply. So they're the long list that we know about. I've just got up here: landscaping, rationing, reduced use, higher prices, things like that. So the first thing we need to do is develop a method for measuring the cost of low levels of reliability. And I think that's a fairly straightforward thing to do. Let me just say there's an avoided cost approach, which I'm going to advocate is practical. There's another approach that economists would take, which is to say, what are the customers within an agency willing to pay to avoid future periods of shortage? And obviously, the avoided cost method is only part of their willingness to pay, because if they're going to actually literally incur these costs in the future, that's a lower bound estimate on the value of avoiding those periods of shortage. Okay, so one of the first things we need then is an accounting framework for measuring the social cost of low levels of reliability. The next thing that we need to do is to actually calculate how much better supply reliability is going to become over this time period, over these 20 years, if we develop this local source. And so one of the things that we need to do is we need to be able to forecast the frequency and severity of years of low reliability without the local source being developed, and then compare that to the same prediction with the local source developed. So we can describe the diminution in the severity or the duration of the shortages that are experienced over this time period. Right? That will allow us to sort of describe how many fewer years and how much less severe shortages are going to be over that time period. We can then take step one, which gives us a per year cost and a schedule of those costs, and then we can apply and take the improved reliability that's achieved through step two and combine those two and calculate the present value of future avoided social costs that are associated with an improvement in reliability. Right? So that's really the fundamental activity that we're engaged in terms of valuing reliability. First we need an accounting framework for measuring its social costs. Second, we need to be able to describe the hydrologic and the supply improvements that would come from the investment in the local source. We need to take this stream of cost and this stream of hydrologic outcomes and somehow discount them back to the present so we can think about different investment opportunities. Okay, so that is essentially how I would suggest valuing reliability. Now there is this second value component that could come from developing a local source. And the approach that I'm taking here is much, much more standard. This is in no way a contribution of any sort, but it's an important value component to developing local water sources. And it arises from the fact that in most cases, the cost of developing local sources is going to start off high and it's going to decline over time. And the cost of imported water, for a variety of reasons we can talk about, is increasing over time. Right? And so one of the things we want to ask ourselves is, what is going to be the net cost to ratepayers or customers of investing in that local source, which is going to displace the need for imported water? Is it going to cost them money over the period of the planning investment, or might it save them money? Might it represent a cost savings, right? And if we think about our canonical example of desal and imported water and NWD's water rates, this is sort of taken from the 2010 Integrated Resource Plan, we can see that after a period of fairly stable costs, over the last 10 years, there's been an increase. And with even a modest 5.5% to 6.5% increase a year going forward, as energy cost agreements expire and energy costs go up, as maintenance cost goes up, as we overlay the delta fix on the unit cost associated with it, even a modest 6.5% a year means a doubling in these costs over time. And so the question arises, compared to local sources, will there ever be a crossing point? Will there be parity between imported water and some of the local source developments? And the way an economist thinks about this on behalf of ratepayers and customers is we want to know over a time period, if you've got a local source that the unit costs start off quite high compared to the backstop cost of imported water, but there's a point of convergence and then a crossing. Let's see here. We essentially want to take these costs, which are borne by ratepayers, and represent them having to pay higher costs for this desal water, which is displacing the imported water. And we want to ask, are these cost savings over here, is the discounted value of that greater than this? Right? That's the calculation that you want to undertake. And if they are, the local source represents a net cost savings to ratepayers. If they're not, it's another source of financial cost that they're going to have to bear, right, associated with the development of the local source. So let's start off assuming that we're getting a revenue flow from selling this water. In addition to that revenue flow, there's the present value of the reliability benefits, which are actual financial benefits that come from avoiding experiencing the low levels of reliability. They're the adaptation costs for the agency. They're the adaptation and lost welfare costs to customers, plus the present value of the avoided cost. And we don't know whether that's going to be positive or negative, right? That's an open question. We don't know how big the reliability costs are, but at least we have a method for calculating those. And then we can undertake the traditional capital and O&M calculations of figuring out the levelized cost of a local water source in terms of its productivity. And then compare this overall, the value proposition of this investment with others. And I think that if we do this, what we're going to be able to do is begin to incorporate some of these values, like the value of reliability, that have been overlooked, that are moving to the forefront as we, as a region, deal with greater and greater variability in supplies due to regional shortages, El Nino effects, and a variety of other things that are happening. And with this kind of approach, we can answer questions about which policies to invest in first, what's the optimal size, what are the true ratepayer costs going to be over the lifetime of the program, and lots of other practical things, and evaluate the benefits, and quantify and measure and communicate the benefits of reliability associated with different policy options. Okay, thanks. I'll take some questions at this point. I'll let my moderator arbitrate the questions.
All right, I'll arbitrate. Okay, here's one right here. Mark. Mark, you're first.
Thanks for that, Javier. So when you're trying to calculate the bottom line here, each one of the elements of that, reliability, investments in capital, O&M, and so on, there's different degrees of uncertainty associated with each one of those, right? How do you, and particularly when you're trying to quantify reliability, I mean, how do you, which has got its own error bars on it. How do you kind of wade through vastly different degrees of uncertainty associated with each one of those elements?
Well, it's a great question. You really want to narrow down the sources of uncertainty that you're interested in. I think the first thing is you want to identify where you think the greatest sources of uncertainty are and explore the effects of that on your decision. So we might think that we really don't understand both what future cost and the future supply variability of imported water is going to be. And so we could take a local source and we could assume we have a reasonable guess about what the local energy costs are going to be, what its productive capacity is going to be, and in the context of a water agency's pre-existing portfolio, we could look at what the reliability benefits are under different scenarios associated with imported water, right? So you could have imported water falling by a half, falling by 25%, falling by 10%. So that's one way to begin to unpack it, is through scenario analysis. Really trying to prioritize the sources of uncertainty that you think you face. And maybe you think that your biggest source of uncertainty isn't imported water, but it's the cost of energy. Well, you can do the same kind of analysis and let energy factor through all of these options and look at the net benefits in that context too. So it would be sort of a prioritization and scenario analysis approach.
Okay, so next question be back here. It's coming. It's right behind you. Almost there. There you go.
As I understand the MWD current drought allocation structure, is they look and say they offset local supply anything that they have put money into. So if you locally built a desal plant and you spent $700 million doing that, and you had 50 MGD of supply, as I understand, roughly 90% of that is offset when MWD allocates water to you. So there's very little additional reliability given to the entity that pays for it, because that's the way it is. So you're subsidizing the whole system and getting very little benefit. Plus, in your analogy there, when MWD spends the money for the Delta fix, hopefully that sometime happens, their reliability goes up dramatically, hopefully. And how do you put that in? Because, I can't ever see a crossover when you're dealing on energy, desal plants at 50% energy cost, and that's long-term contracts for water are down in the mils per,
Until 2017, yeah.
Well, their
for some of them.
Hoover Power went, 30 years? 50 years? And that was for, one and a half, 1.5, 4 mils per, kilowatt hour? That's a long time.
Yeah.
It's long beyond my level of relevance here.
Yeah, so I think the overarching focus of your question really is, would the value of this reliability actually be positive? Would it be significant? Would it be large? And clearly, if the Delta fix results in dramatic decreases in the cost of imported water and also increases the quantity and minimizes the variance of that water, sure, you're going to see very, very, very low benefits to local development. Whether it never crosses over, I think I'd probably challenge that, because even we have a lot of technologies to become much, much more efficient, and I understand that right now whatever we're at, $800 an acre foot. It seems low, but it doesn't have to compound at a very high rate before it increases. And if you look at the cost of new technologies and how they've been changing over time, once they start to scale, take solar, take batteries in electric vehicles, for solar we've seen decreases of 18% a year in those costs.
But
so
this is the point, that their variable cost is $210 treated versus $1,800 treated for. that misses the point that the variable cost, which is generally what you compare a cost on, is roughly $210 an acre foot for MWD imported water versus close to $1,700 currently for.
You're absolutely right that you need to look at those input costs, and significant differentials between those input costs are going to change these calculations if they persist. There's no doubt about that. The question is, I think we need to run the numbers before we come to conclusions and look very carefully at what cost trends have been and what those factors are going forward. I'm not suggesting this isn't an argument for local source development. This is a proposal to do the math so that we have some sense of what the sources of uncertainty are, what the key cost drivers are. If it turns out that the differentials in the input costs are hugely deterministic, then we'll know that. And local agencies can take that into account as they're trying to figure out whether to diversify or not. So I'm simply trying to bring some transparency and a way of calculating the benefits, if they exist, of local source development.
One more question, perhaps? Okay, here it is, right here, right here.
You told us that if we asked you, you would tell us why water recycling is moderately sensitive to long-term droughts.
It's simply the recognition that the quantity of wastewater produced declines and the cost of treating that wastewater to reusable levels increases. And so
I guess I'd challenge you on that, because I don't know of too many water districts that use all of the wastewater available to them, and I don't know of cases where the wastewater strength becomes significantly higher during times of drought. It seems to me like most of the savings are for outdoor water use, and that doesn't make it back down the sewer.
I certainly wouldn't want to, without doing the analysis, rule out wastewater recycling. I had it on there as a possibility. So it's again, my argument is, let's actually do the analysis. Let's put our assumptions on the table and let's have the conversation about what those costs are to the best of our ability. Right? We've really, a lot of our conversations have been conjecture. We don't have the cost inputs. We are not actually showing each other our models. Let's do that and have that conversation. So I didn't mean to in any way actually argue that desal would work, that wastewater recycling would not work. My argument is, let's actually take this approach. Let's value reliability. Let's value the avoided costs, if there are any, and compare apples to apples.
Okay, let's wrap up this one. Thank you very much, Dale.